Thank you very much, Mr. Chairman, for your kind introduction, although I didn't understand really Portuguese, but I assume he's really a gentleman. Anyhow, so my speech today is about something which is quite important really to all businesses, to all industries, although people take it for granted, lubricating greases. We are base oil manufacturers, one of the largest naphthenic oil manufacturers. So our job is to support our customers wherever they are and in a way doing part of their homework. So we have laboratories for different applications, including greases. So we do our own samples and characterize it. And in this kind of forum, try to present it and communicate it to the audience and people who are interested of knowing a bit more. However, it is just the top of the iceberg. If you would like to discuss this kind of issue with me or my colleagues, we are available during these days. The title of my presentation is The Impact of Naphthenic Oils on the Characteristics of Lithium and Lithium Complex Greases. So I'm going to start to introduce you to talk only to show you 3 slides from NYNAS, and it's not advertisements really, it's just about who we are and what we are doing. Then background to the project, what is solvency, experimental work, and at the end with 1 page, 1 slide, I will summarize the job. Okay, NYNAS is a very different company. Although we are an oil company, but we are different compared with all other bales, oil companies. Most of the oil companies are fuel-driven companies. In our case, fuel is a byproduct. This means that fuel is not really important to us. And now when we are moving towards electrification, for instance, we are not going to be hurted by that. Why? Because we are not producing too much fuel. Our expertise, however, are focused on bitumen and base oil. So the next 2 slides will show you some of the applications where we are deeply involved. Chemical industry, industrial rubbers, adhesive, battery separators, printing inks, explosives, fertilizer. This list could be really much, much longer. And then we move to tire industry. My colleague Gutenberg is going to talk about that tomorrow. Then we move to lubricant industries. Of course, we have lubes and greases, metal working fluid, hydraulics, gears, and then electrical industry. We are world leader when it comes to electrical industry. This is the only application where we promote and sell our products fully formulated, which meets national and international standards as well as industrial standards. All right, the focus of this talk, of course, is lubricating greases. About 2 months ago, less than 2 months ago, I had a presentation in US and at NLGI conference. And at that conference, every year, they provide us with the latest production survey. Sorry, I don't want to test your eyes. Don't try to read it. But I just want to show you that this kind of data are available. So what you see here is that more than 2 billion pounds, 2.5 billion pound grease is produced worldwide. And if you translate it to kilo, then it's about maybe 1 billion kilo. So it's lots of greases which are produced. If you look at the thickener types, we can see that lithium and lithium complex greases stands for above 75%, and then followed by calcium-based. In this case, we have a number of different thickener technologies, but all have something in common, and this is calcium. Then we have polyurea. Japanese are fantastic in using polyurea in many applications. The production, in fact, in Japan is above 26, 27%. What about Caribbean, Central, and South America? If you look at this chart, you will see that instead for 75%, which was total production of lithium and lithium complex greases, here we have, sorry, the number is not visible, but the number is about 86%, so it's much higher, followed by sodium grease. But anyhow, what I showed there can be summarized in this slide. If you compare the world production with what is produced in this area and your neighborhood, exclude, of course, North America, you will see that lithium and lithium complex greases represents more than 85, 86%. And you have to remember that all grease manufacturers have not maybe reported the data, their own data to the organization. However, 99%, almost 100% of all greases which are produced in this region is based on mineral oil. And that's the aim of this study, to focus on the usage of mineral oil, because naphthenic oil is also, as you know, a certain type of mineral oil, and lithium complex greases. So we are covering really the big part of this cake. So the aim of this study is that really pick up two naphthenic oils, which have same source of crude. We use same process in order to refine it, but they have been refined differently. The more refined oil, the lower solvency, the lower polarity. Then we made lithium and lithium complex greases. In the complex greases, we used also two different complexing agents. All right, starting with solvency, because solvency is the key issue in this presentation. And I think one of the papers today, it was also about lack of solvency in group 2 and group 3 and how additive suppliers can help customers with that. We improve solvency. If you look at the refining is simply purification. So we try to get rid of lots of impurities, although we can take out everything, but it is not economically adjustable. So what we do, we take as much as possible, because if you wait too much to take out everything, you lose flow and thereby money. So the idea is to keep carbon and hydrogen. So the degree of refining is equivalent to degree of solvency. For instance, white oil, or if you go to paraffinic oil, group 1 and group 2 and group 3, the more you move from group 1 to group 3, the lower the solvency is. So because you purified it more and more. So, but it has some consequences to our industry, lube and grease industries. Solvent power could be defined as the ability to solvate other molecules. Solubility is the ability of being dissolved by other molecules. For instance, if you look at the additives, many additives contain maybe 10, 15% active added components, and then the rest is carrier. If you have a carrier and oil with high solvency, you can dosage that additive package with more active additive, which means that you can sell more concentrate product. So it's very important. Here, a list of some of the applications where solvency is the key. And of course, when it comes to the greases, the thickener content is one of the issues which is related to the degree of solvency. Okay. And solvency, when you look at the product data sheet, solvency can be read off by look at the annealing point, or viscosity gravity constant, which is a dimensionless number. I'm coming back to that. Annealing point, if you look at the type of the oils, aromatic oils have high solvency, but they are toxic. So they are not allowed to be used, followed by naphthenics and then paraffinic. However, there are areas where the solvency of naphthenic and paraffinic could be the same. For instance, if you look into the white oil, naphthenic white oil, and typical paraffinic group 1, they have more or less same annealing point. Viscosity gravity constant, this is also a number which you see often in your product data sheet if you ask your supplier. This is a kind of as I said, calculated number, which starts from 0.76 and end up with 1. So the higher, the higher solvency. Okay, experimental work. So as you know, conventional greases typically consist of 3 components. Mineral oil, fatty acid, often 12-hydroxyesteric acid, sometimes HCO, castor oil, hydrogenated castor oil, and of course, lithium hydroxide. So the indication of you make a lithium grease is that the dropping point should be above 180. If you look at the lithium complex greases, you introduce a 4th component to this matrix, and it is a complexing agent. And by adding that complexing agent, you increase the dropping point to above 260, which means that this product could be, this type of product is more suitable for high temperature application. So complexing agent could be acylic acid, could be sebacic acid, boric ester, boric acids. Number of options are on the table. So these are the 2 oils which we have used, T110 and S100B. T110 is the product which contains, it has higher solvency, less refined than S100B. S100B is the technical white oil, but they have same crude, source of crude. If you look at the numbers, first of all, you can see the viscosity are in the same range, as well as the flash point. The pour point is very low, -30, and the reason is that the crude that we have used is wax-free. So we don't need, in fact, in our refinery to have the waxing unit. In contrary, when you look at the paraffinic oil-based refineries, they should have, or they have often, almost always, the waxing unit. Then we look at the color. Colors are quite light. Last but not least, as I said, if you look at the annealing point as an indicator, you see that the annealing point of T110 is 87, while S100B is 104. So it means 104 offers lower solvency. And also aromatic contents. Aromatic contents very often has been used as an indicator of the solvency. It is correct if you compare apple to apple, if you compare same type of oil. For instance, if you compare paraffinic with naphthenic with the same viscosity, even if they have same aromatic content, naphthenic oil has high solvency. Why? Because naphthenic oil contains also cyclic molecules, type pentane. And these contribute to the high solvency, but it cannot be counted as a aromatic. So we made 2 different greases, or 2 lithium greases based on these 2 products. First of all, we can see the soap content is, the soap content for T110 is lower than S100B, which is also reflecting the better polarity and solvency. And then we can see that the dropping point above 180, so it is a lithium grease. And then, of course, the mechanical stability, which can be read off from penetration after 100,000 strokes and so on. And since we have removed most of the sulfur, active sulfur in our oils, you can see that the copper corrosion is 1A without having any copper passivator, which is very often used in grease and oil business. Here I would like to give you a new definition. I introduced this last year. One way to see the benefit of using naphthenic oil in grease is, okay, look at the thickener content. Thickener is often more expensive than oil, and then you can calculate how much you save money. But you can look into that from different angle. I call it increased productivity index. Let's see, if you look at how lithium grease is produced, you have mainly 2 steps. The first step is a cooking stage. It is in blue color. And the second step is cooling stage. The first step, as you can see on this chart, this is the most time-consuming and expensive part of the process. The first kettle or reactor is very expensive to set up because it has to be jacketed. You have to go up to about 200 degrees C. You have to wait maybe for 4 or 5 hours. So the point is that this is the bottleneck of the process, simply. So what I would like to share with you here is that by using naphthenic oils, really, you can increase your productivity without spending any money into the steel and responding to the need of the market immediately. This means that in the cooking kettle, as I said, you have lots of limitations. One of the limitations further is that the concentration of the soap which you start cooking your grease here is limited. It's, for instance, 20%. And then you add maybe 10 additional percent, 50% more oil in the cooling stage, and then you get a finished product which contains 10% soap. It is the case for paraffinic oil. So this is the case. Assume that you are going to produce 1,000 kilo grease, and for that you need 10% soap or 100 kilo thickener. So you end up with a yield. This is easy to calculate. You can calculate for any type of oil, including T110. So you end up with lower thickener content. But if you divide one to other, and this is the new thing, which I would like that if you are dealing with the grease, remember that. This increased productivity index should always be above 1. If it is below 1, then you lose money in the production. We are focusing traditionally too much on the formulation, not on the production and formulation. Here is the point is, if you can easily increase your productivity and prove it within 1 or 2 days by just playing with the oil. Or if you use blend of the oils, still you should be able to find out the yield and subsequently the ratio between the current yield and the yield that you had last week and come to this conclusion. The assumption here is that you end up with the same product and same quality. This means that if you go through this calculation and based on these two oils and having paraffinic SN500 as a reference, we will end up with T110, something about 30% higher productivity. With other words, if someone makes 5 ton grease per day, and by just playing with the oil, he can increase up to 2,000 without putting in more manpower, without putting new facilities or new process pipes or lines. To me, it's lots of money, really. And I haven't even talked about the fact that every kilo of grease which is sold, grease makers get a revenue. So there is, on top of that extra revenue if he starts to sell this product. But this means also that instead for a week, 7 days of working, so he can still produce equivalent to 7 working days with 5 working days, and so on and so on. Okay, now I move to lithium complex greases. So we use 2 naphthenic oils, as I said, and the other part is that we use 2 decarboxylic acid, 2 complexing agent. Without complexing agent, it is not possible, to my knowledge, to make a proper lithium complex greases, which can stand against a high temperature. Very often, manufacturers are finding a kind of shortcut. There are additive suppliers who are offering boric ester, for instance, which you can put into your lithium grease and get a lithium complex grease. But there are also lots of concerns about the quality or characterization of those products. But anyhow, so what we did was going through a number of test methods. I'm not going to go into the details, just a list. And what we did also, taking out some electromicroscopic pictures. So we have 2 categories of greases. We have grease A and B, which have been used, with respect to a certain decarboxylic acid with a shorter chain. And it has also lower melting point. And the other one, acid G, has longer chain. Since the focus is the oil and not the carboxylic acid, I just jump over those. But if you would like to ask me afterwards, so I can certainly discuss it and further. So we used 9.5% soap. We wanted to reduce the risk of or sources of deviation. So we used 9.5 thickener, and then we decided to read off the consistency at the end of the day. And as you can see, first of all, the dropping point more or less is around 300 or above 300, which is great. The product is grade 2 when it comes to the A and B. This consistency tells us that the product is NLGI grade 2, but when we change the carboxylic acid, we get thicker product. And if you look at the oil separation, we see that oil separation is a bit higher here. It's almost double as much as these. I can discuss also later on, hopefully, a bit of the importance of oil separation in the application. And this has been affected certainly of the consistency, because here you have lower consistency and it blocks the flowability or reduce the speed of the movement of the oil when it is exposed to the heat under this condition. But also the type of fibers we make based on different carboxylic acid affects that. Last but not least, we see that oxidation stability at 100 degrees C is better. Let's see if I can come to that. Oxidation stability is much better for the white oil, technical white oil, compared with T110, S100. The reason is that since we had a small amount of antioxidant, we know that the response of the additives and antioxidant is better in the more refined oil. So if you add this certain amount of antioxidant in paraffinic group 1 and paraffinic group 2 or 3, you get certainly better result in group 2 and group 3 compared with group 1. And here we see also. The other part, what we see here is that these numbers are double as high, twice as high as these numbers. So it can be maybe related to the type of the carboxylic acid as we use as a complexing agent. So the conclusion here is the consistency of T110 and acid G, the carboxylic acid with longer molecule chain, showed best performance. From the oxidation point of view, is the opposite. We did also the softening test of the greases, because customers, time to time, they store the grease, and of course, we exaggerate the role. Whenever you have 120 degrees C in your store department, but here we went up to 120 degrees C and measured the changes. And we could see that all the greases are changing moderately up to 80 degrees C. When we move from 80 to 120, we see that T110, which has higher polarity, shows less softening compared with S100B, although it has lower thickener content. And it is regardless the type of the carboxylic acid. So here we have to highlight the role of the polarity or solvency power of T110 compared with S100B. We took lots of pictures. You know, when you take same pictures from greases, first of all, often, traditionally you have to clean or to wash out the oil. So you affect, in fact, you treat the sample and then thereby you affect the texture. And the other part is that you can always discuss that small sample, does it representative to the whole bulk of the grease batch you made or not? With respect to those source of errors, we can see that the upper parts are thicker, the fibers are thicker than this. However, we see more dense structure here compared with here. This suggests that, first of all, it affects the oil separation of the product. The other part is that it affects probably also the consistency of the product. So we got thicker product, in fact, when you use acid G instead for acid R. Oil separation, typically when you run this test, IP 121, the test time is, the test condition is 40 degrees C, 168 hours. And what you check is the separated oil in the chamber on the bottom of the sample. The problem here is that traditionally, unfortunately, many grease manufacturers or users are looking for as low oil separation as possible. But this also means that they jeopardize the lubricity or the degree of the lubricity of a grease, of an application where the grease is going to put in. Because we know for sure that the at the end of the day, is the base oil which lubricates, although the thickener also participate in the lubrication. When you do this kind of test, you will see that most of the oil has been separated within 48 hours. According to a study which we performed for a number of years ago, and even SKF has done it, they came to the conclusion, as we, of course, that we have two types of oils involved in greases. Bonded oil, the part of the oil which you use in the cooking stage and the initial cooling, and the last part of the oil which you add during the cooling and adjusting, which we call it for non-bonded oil. And that non-bonded oil is leaking out first. So, and that non-bonded oil is a kind of guarantee for the lubricity or the lubrication over a long period of time. So when the non-bonded oil has been consumed, you may end up with starvation or dry lubrication. So with other words, it is good to use that non-bonded oil in a gentle way. So what happens if I take out this peak? This means that I can extend my lubrication time. So it means engineering in the field can be really critical. SKF, for instance, has a product for windmill. It calls LGWM1. Has an oil separation of 8 up to 11%. 8 to 11 is high, really. Normally, it should be below 5%. Why do they do that? Because they want to use one product regardless if it is in wintertime or summertime. So they use this product in Nordic countries and quite successful and has very long life. So oil separation, there are different views to discuss, and I could stand here and certainly take a number of hours of your time to discuss it. But it's extremely important to understand where the product is going to be used and what is the requirement of oil separation for that specific application. So these are the oil separation over 15 days, which we have done. Normally is 7 days. We extended. What we see here is that T110, in fact, shows best result because of the high polarity or high solvency that we have discussed as well. We did also elastomer compatibility test. We use chloroprene, and the compatibility with the elastomers is very simple. All molecules migrates in, and the plasticizer, for instance, additives migrates out, and subsequently you affect the last transition temperature of the rubber, hardness, tensile strength, and so on and so on. For many applications like CV joint in automobile industry, you need a certain swelling effect, not shrinking, because otherwise you get leakage. So often a certain swelling is required. So depending on the applications and type of elastomers, you may use different type of oil and additives. Here we did number of tests, and what we can see here in this study for these two oils, S100B, the technical white oil, affected or was more suitable. We did also low temperature mobility. It's extremely important, although here in Brazil you may realize that in this temperature, this is winter. In Sweden, it is our summertime, so you don't need it. But the bottom line is that if you are making a product in order to fulfill OEM or a specification, it could be your competitor product which is coming from the other countries. And they are stating that our product is mobile from, let's say, -30 up to whatever. Often is the low temperature is a problem, not high temperature. So we use this test method. It is a German accepted test method. I assume most of you know that. So what we did, in fact, we exposed this down to -40. It's amazing that the naphthenic oil can even be mobile at -40. What we see also that the greases which are thicker in consistency show less mobility or needs higher pressure in order to move inside the pipe compared with the thinner products. Perfect, I have 2 minutes. So, summary. If you look at these two types of oils which we use for lithium and lithium complex greases, with other words, 86% of the product which are produced in this region, it is covered by this paper. So what we see is that from a soap content point of view, a product with higher polarity like T110 is more suitable. It also showed that in comparison with, for instance, paraffinic oil, SM500, it can offer also increased productivity with 30 or 40%. I'm not arguing whether it is 25% or 40%. The point is that you get an increased productivity, which is extremely valuable to your business. The other part is in productivity in oil separation. We see lower oil separation in technical white oil because simply we had better structure. Compatibility with CR I showed here, it was not as good for T110 as for S100B. But if we choose NBR, nitrile butadiene rubber, which is used for CV joint application, then it's the opposite. That T110 is better than S100B. Flow pressure, more or less, is the same, depending on the consistency. Oxidation stability is better for the white oil because it has been more refined. Last but not least, the cost. The cost of more refined oil is higher than less refined oil. If we look at the complexing agent, we see more or less plus and minus. I don't go through the all, but what we can see is that the cost here could be beneficial. I know, for instance, in China, they prefer, in Asian countries, they prefer to use decarboxylic acid with longer molecule chain, partly because of the availability and partly because of the price. So with those words, I thank you very much for your attention. And here you have my mail address. If you would communicate and discuss anything, so please let me know. As I said, it is just the iceberg of what we usually do within the lube and greases. So with those words, I will show that I don't have I take any responsibility for what I said here. So, and there are a few references, among others, the paper which I published at NLGI a couple months ago, or less than a couple months ago. Thank you very much.